capacitive touch sensing. At least I think that's right. It should be lab 6. And so we'll do that. And the touch pads are the UTSA letters on your board. And so you'll program those. And I'm trying to remember if we modified the lab to cover all 4 letters. I think we did, but I don't know. Maybe not. Hopefully we'll get that working. Maybe I'll look at that real quick and see. So I'm going to be out of town on Thursday and Friday at a conference, and so we're going to do a test on Thursday, and then the standard lab on Friday. But I won't be around for that. So let me just look at that real quick. I'll take another look tonight. Let's see. But I think it's. I can't remember. Traditionally the boards we used for a number of years only had 3 pads, and then we added one this last summer when we made the last round of boards. So I can't remember if we put that into the code for the fall or not. Times 6, times 6. Let's see. What it should say. Make not have. Yeah. So the pads are labeled. So I'll see if I can edit this and maybe fix it. The way I think these are the same pins, but of course the pads are labeled differently. The one constant in all this, though, is you can look up here at this initial document that says Viva board pin revision 4.3 pin outs, and so this does give you all the correct info for the board, for your board. Yeah. Oh, you don't see it. So here's this document. So it's located on Blackboard at the top of the lab page. So you just click on that, Viva board revision 4.3 pin out. So that's the board you have. And so if you look through, you can see here the UTSA pins are RA4, RC7, RC1, and RC0, which correspond to capacity touch sensing 3, 9, 5, and 4. And I think if we look at the lab, let's see, did I kill it? Oh, maybe, let's see. So if we go down here to lab 6 and I look at that document, so if I can, I'll fix that before Friday. I may not get that done. We'll see. So right now it's RA4, RC3, and RC7. So let's see how that compares. RA4, RC7. Let's see. RC3 and 7. Yeah, so there's RC7, but RC3 is, so we changed RC3. So the pins are a little different. So I'll try and fix the lab description. I guess I didn't get it fixed last fall. Sorry about that. Anyway, so we'll fix this up and make it correct. And also, so the RB7, I did change that. So the push button, well, no, actually that's this document. Never mind. Anyway, so we'll work it out. I'll try and fix the lab before you guys actually get to it. Let's see what else it's going to do. Let's see. So in this lab, let me just make sure. In this lab, we write a C routine using the XDA toolchain and MPLabX will use touch sensing with the capacity touch sensing module. The principle used for this is very simple, but the steps to set up are complicated. For this reason, most of the setup has been taken care of in functions for you. The goal of this lab is to give you a setup, basic operation code, which you have is to work out the threshold value required to make the program functional.
Yeah, I'm talking about.
So every one of these touch pads could have a different threshold, although typically one threshold works pretty well once you figure out where the division is between touch and not touch counts. And we'll explain that when I go over to touch sensing in just a minute. Anyway, so we'll use 4-channel touch sensing, and we'll set all this up for you. And let's see, we'll also use the UART with the USB dongle, and probably not Bluetooth. We'll probably use the TTL level dongle that fits on your board. And you'll hook that up and see that in PuTTY on your desktop or laptop. And the reason for that is you need to see what the data is, what's actually being sent out, and it's really nice to have a TTL connection, a UART to TTL connection to USB, so you can actually see the numbers. Otherwise, you'd have to use the debugger capabilities, which you can do, and that works fine, but it's a little more convenient to have it printed out from the program onto your terminal program running PuTTY. Okay, great. Yeah, I don't think there's yeah. So this explains the UART, and we'll set it up, and you'll see we'll have these thresholds printed out like this, and basically once you see what it is, what the count is when it's not touched, and then you see what the count is when it's touched, then you see the threshold has to be between those two numbers, and then the way the program works, you compare the count for the touchpad to the threshold, and if it's lower, then you know it's touched. If it's higher, then it's presumably not touched. And again, we'll explain that in just a minute. And this also recapitulates the capacitive touch sensing principles. So that kind of goes through it, and you can read this. This will help, and I'm going to talk about it here in just a minute. And then this gives you some of the program. But I'll fix all this up so it correctly lines up with the current hardware. Because right now it's set up for the old boards. All right. Okay. So I'll fix that. All right. So that's for Friday. So Thursday the test, Friday the lab, touch sensing lab. Okay. Let me talk first about the touch sensing, and then we'll kind of do some review for the test. And I might talk about the homework too, although I looked at the homework, it's pretty straightforward. But remember, I think it's chapter 4, homework 4 is due tonight at midnight. Okay, capacitive touch sensing. So first off, I think I mentioned this somewhat tangentially before, but why do you think, what do you think is the big push? Why have many consumer electronic devices gone from mechanical switches to touch sense buttons and other types of touch sensing? Yeah. What's that?
Less hardware?
Well, so yeah, I mean, so let's think about it. So if you have a mechanical switch, you know, you have some kind of a circuit, and you know, and here's your switch. Okay, so that's not a tremendous amount of hardware, is it? Really? On the other hand, for a touch sensing button, you have a little pad on a printed circuit board, and then you have a trace that goes to a micro, and then this microprocessor's got you know, some kind of a touch sense module that's connected here with, you know, a big analog multiplexer, so you can select several different touch pads. And then you've got firmware that's running up here, and then you have to have some thresholds plugged in, maybe a different threshold for every button, and yeah, I don't know. It looks like maybe there's more hardware here.
Convenience for the common man.
Well, let me just say this about that. I'm a real believer in touch buttons. I think they're definitely, that's what you're going to be designing in most equipment, no question about it. But when I think of touch buttons, I don't necessarily think convenience. What I think of is my refrigerator. I have a Samsung refrigerator, nothing against Samsung, and it has a touch panel on it to turn it on and off, to set the temperature, to dispense ice and dispense water, and the new child locks and a bunch of other stuff. And it sits in the corner of our kitchen, and it's a black panel. It has some blue LEDs that light up in somewhat random, confusing ways that I don't understand. And then it has little teeny print, some of it printed vertically, so you have to turn your head to the side to read it. And some of the buttons, if you hold them for 5 seconds, do things like turn the whole refrigerator off, with very little warning on the panel that that's what you just did. And then it does make these little bink bink sounds every now and then that are not tightly correlated with anything you're actually doing. And then you have to sort of hold the button until your thumb goes numb for some of the functionality. So I don't really consider it a convenient, right? So convenience for mankind? Not really, not in that case. Give me some big old toggle switches. I would have preferred those. However, I do believe in touch sensing. I just happen to believe that interface sucks. Whoever designed that engineer, I'd like to give him a piece of my mind, or her. I'd like to, but I probably have to chew him out in Chinese or Japanese. That probably wouldn't go very far. But in any event, so if you do a bad job on an interface, it doesn't matter whether it has fancy touch buttons or whether it's got, you know, two-hand, you know, crowbar throw switches. It's still gonna suck, right? You can do a bad interface with new technology, and you can do a bad interface with old technology. So it's about a lot more than that. But you haven't really gotten to the reason why people use touch buttons. Yeah.
It's easier like to fix, so like if your fridge broke and I wanted to remote, since it's new and say like you had Wi-Fi to remote in, instead of having to actually be there and touch the buttons, I can, you know, do all that online through remote, like remote in.
Yeah, maybe so. Probably so. Yeah, that's a thought. Yeah.
Less mechanical wear and tear.
Now you're getting to the heart of the problem. Mechanical switches are actually rated, and one of the specifications they're rated for is, guess what? How many times you can actuate the switch before it breaks. Meantime before failure for a mechanical switch. Mechanical switches break. Mechanical relays break. Anything mechanical breaks. Touch buttons break too. But when they break for other reasons. They break because lightning struck your electrical pole outside your house and blew the electronics in your refrigerator. And now you're going to have to put in a whole new board, and nothing else works in the refrigerator anyway. So it's not like just one switch went out. Yeah, and the other thing is, you know, but you still really haven't gotten to the heat of the matter. That's one of the reasons, but that's not the big reason. Yeah.
Because Apple was really successful in everything they did, and somehow convinced everybody to start using these things.
No, I'm not going to give Apple that much credit.
Suddenly it was successful.
No, I mean, Apple's using touch screens, you know, touch buttons. Yeah, I mean, yeah. If you like me, you hate, you know, you love your iPad, but you also hate it because it doesn't have a USB port on it. And why they thought that was a good idea is beyond me. No, but it's really not that so much. No, it's just a lot more basic than that. You're sort of aiming too high.
Expenses.
Yes, yes. So let me do the math for you. Now, I know the thought was, well, more hardware, you know, with switches. It's not more hardware actually, but it is more cost. So this switch could easily cost in large quantities. If it's a really nice switch, it could easily cost 25 cents. It easily could. And if you're making millions of these, you may be able to buy this micro for 1 cent. And the printed circuit board might cost you 5 cents. So you've got 6 cents, and you've got 1, 2, 3, 4, 5, 6, however many switches you want. And over here, 25 cents a pop. And that's in quantity. Oh, you might get it down to 20. But I mean, these are expensive. They're not cheap. And they fail on top of that. So if you buy cheap ones, they'll fail at a much higher rate. So you really can't afford to go super cheap on these because they'll just break like crazy. I put a cheap little slide switch in my 4-year-old broke it within 10 minutes. I was dazzled. 10 minutes of screwing around with it, and it was broken. 10 minutes. And now I put another one on, 10 minutes. So at least it's consistent. All right, well anyway, so yeah, the total cost of this, all this additional hardware, it's still cheaper than this 25-cent switch. And what if we have 3 of them? Now we're up to 75 cents. Oh my, we've really saved a lot of money. And guess how much these pads on your printed circuit board cost you?
2 cents.
Nothing! You got the printed circuit board anyway. And whether you have a pad or don't, it's free. Now, you might have to make the board a little bigger. Okay, so now you're paying a few cents for the additional square area of the board. But I mean, not much. But the actual creation of the pad or not, if there's actual room on the board, it's totally free. Totally free. It doesn't cost you a thing. So it is more hardware. It's a lot more hardware. It's an amazing amount of more hardware. And it also needs smart engineers that write the programs to make this work. And it also has some vulnerabilities. The touch module we're going to use on this chip has been completely discontinued by Microchip. They don't use it anymore. And the reason they don't use it anymore, it's got a fatal flaw. If you have interference at just the right frequency, you can't fix it. It will break. It'll always work. It will always prevent it from working correctly. And so it's a big problem. And so Microchip finally gave up, and they came up with a whole new way to do touch sensing. And they stopped making these touch sense module, and now they use their analog to digital converter instead, and they give you software. Software routines, by the way, written in assembler. And you have to use them as they are in assembler because the timing is so critical, they can't write them in C. So, so that's where they are. And they don't use these, they don't make chips with the touch sensing. The new chips don't have this module in them anymore. But they do have better A to D converters generally. And that's been the one thing that's kept me from going to the next level chip, because the touch sensing is more confusing and a little harder to do. But on the other hand, it is a little more robust. For our purposes, though, this touch sensing module is going to work great. It's just that if you're in a noise environment with certain frequencies of interference, it won't work. Okay, so let's look at how this module works. The other modules work in a similar way. They're just a little more robust to fixed frequency noise. So it's not that different. It's just a little different. All right, so we have a bunch of different touch sensing technologies: inductive, resistive, ultrasonic. There's a whole bunch of them. Electrostatic, even, I guess. But we're using capacity touch sensing for this. And the way that capacity touch sensing works, it creates a pad that represents a capacitor. And when you add your finger to that capacitor, you add additional capacitance to that capacitor. And that additional capacitance changes the tune circuit that capacitor is functioning in. And it changes it by making it oscillate at a lower frequency. And so what you do is you have this tune circuit, and the tune circuit's is running at some frequency, and you have a counter that's counting how many clock cycles that frequency is ticking at for a fixed amount of time. And so what you do effectively, you have three things. You've got the tune circuit. So there's probably two ends in there, whatever. Anyway, tune circuit, and then you have a counter that's counting. So this is oscillating, and you have the counter that's counting these pulses, and then you have a time base that creates a fixed interval. So you have a fixed interval. Let's say, for sake of argument, it's 1 second. Of course, let's say it's 1 millisecond. 1 millisecond. So you're going to count for 1 millisecond how many of these pulses you read, and then you're going to display that as a count. And then you're going to erase your count and start another 1 millisecond and do it again. Now, since we normally have several touch pads, what we do is we'll have our touch pads set up over here, maybe UTSA, okay? And then we'll have little wires connecting these, and we'll have a little analog multiplexer that'll just select one of these at a time. So we'll select one, we'll scan it, select another, scan it, select another, scan it, select another, scan it, and then we'll go back and we'll circulate through these pads maybe 100 times per second. And each time we'll generate a count. And that count will represent the tune circuit using that pad, and then the tune circuit using that pad. And since they're similar, about the same size, it turns out, I mean, they are a little different because they're different letters, but it turns out they get about the same capacitance, and they get about the same frequency. So the counts are pretty similar, not identical. But then when you touch them, they drop enough that you can use typically the same threshold for everyone. Although if you really wanted to make it super robust, you'd fine-tune thresholds specifically for each one of the letters instead of a generic threshold for all four. And maybe when I mess with the code, maybe I'll set it up so you can do that. So that's what it takes. It takes all this logic to make this happen. So we actually need two counters. One counter counts the pulses in the tune circuit, and we start and stop that timer using another timer to give us this fixed interval. Because we don't just want to know how many counts over who cares how long, we want to know how many counts over, say, 1 millisecond. And then each 1 millisecond, we're going to have another number, another number, another number. And so those numbers, because they're only counting for 1 millisecond, give us if that number changes, we know the frequency of this tuned circuit changed. If we were just counting over various intervals, we wouldn't know what the number meant in terms of relative frequency. We have to have a fixed interval for that to make sense. So we use one timer for the fixed interval, and we use the other timer to actually do the counting. And in the PIC, in this chip, they cleverly set up timer 1 and timer 0 to work together in this manner, because timer 1 has a gate that allows you to turn it on and off, and that gates can be connected directly to timer 0. So timer 0 can start timer 1 and stop timer 1. And during the time that it's running, we get a count. And then we reset it and do it again for the next letter, and reset it and do it again. And we do this hundreds of times a second. Yeah?
So is there a specific count that we would have to like specify?
So the circuit generates the count. What you have to specify is when it's touched, you'll get one count. It'll be higher. I mean, it'll be lower. When it's not touched, you'll get another count that'll be higher. And although the count may vary by, by 100 or so, they're hopefully maybe be 1,000 apart or 400 or 500 apart. So you can pick a threshold between the two counts that determines when it's touched. And it actually turns out, if you really want to get fancy, the more flesh you mash on the button, the harder you touch it, the more capacitance you add, the lower you drive the count. So you could actually scale it for lightly touched, firmly touched, really mashed. But we haven't put that into this lab, but you could do that. And some people in their projects actually use that feature of the touchpads to actually be able to touch them in different ways to get slightly different effects. And that's one of the things about these programmable, dynamic, computer-driven with firmware buttons. You can do more than just, it's not just a switch on or off. It's actually can be more complicated than that. And what's really nice is you can actually, the way they have it set up now, you can put guard pads around these, and you can put a box so as your hand approaches the button, the computer knows you're about ready to touch it, and it's paying more attention than maybe it would have. Or you can actually have just the approach of your hand start some processes in play. Maybe like, I don't know, whatever. Play a tone or something, I don't know. And so when you actually touch the button, then it could click the tone off. So, just to alert you that you're about ready to, make an input or something. And then they've gone even beyond that. Now we have gestures that you can make with these pads that sense the presence of these proximity detectors. You can sweep your hand by one way, sweep it by the other way, have various things, and you can actually do gestures based on these. Yeah?
So would that this is gonna be a weird question, but do humans have their own kind of frequency? Because I figured I don't know, a chair might have frequency too, or am I being dumb?
Do you really want me to answer that?
Yeah. I'm assuming there's no
Yeah. So everything is a partial conductor. Okay. There's no perfect insulator, but basically some things are much better conductors than others, and some are much better insulators. So the human body is not a great conductor, and it's not a great insulator, but it does provide enough conduction to add capacitance to a touchpad. And if you touch it with a piece of plastic, it adds almost no capacitance. You get no effect.
So in effect, you can make it work for certain things.
Yeah, right. Yeah, you sure could. Absolutely. And that's where we have, we now have these three-dimensional gestures. I don't know, they're putting them in automobiles. Does anybody have a car that you can gesture to your radio? Don't actually have to touch and turn a button? Not yet. It's coming. It's the next thing. So when you guys design these things, you're going to be dealing with gestures. I guarantee it. It's here now, and people are going to demand that those be in their products for various reasons. I don't even think we've figured out how to use them effectively yet, but it's coming. Yeah.
If we can do it with gestures, can they just project a touch screen and you would.
Well, sure.
change
So,
it, but the actual
so
configuration
if,
itself-
obviously, if the touch screen, if, first of all, what we have here are pieces of copper on a printed circuit board. Okay, so we can, they're fixed.
Right.
But if, on the other hand, you have a display, and on top of the display, you have a touch sensing device, then you can create buttons wherever you want, and you can define them to be however you want. And you can have big buttons and little buttons, and then you know if the person's touching on the touch sensing surface, whether they're touching the button or not. And then if it has the capacitive or inductive capability to sense gestures, then you can add that feature too, and a lot of other things. With these copper buttons, you can do some proximity detection with this, and Microchip's got, they have a software available for you to use in the libraries to pick up gestures. And what they typically do is they'll put say the buttons in a field like this, and then they'll have around it this guard button, and maybe the guard button's like that thick. And so the proximity detection works off of this box, and then the individual buttons are within the box, and they also have their own individual touch. So as you approach this, it's this big loop that's picking up your gestures, and the little buttons are picking up whether you're touching the button. All right. Well, anyway, let's keep going. I guess we need to finish this so we can review. So anyhow, this is the idea. Okay. So there are a lot of benefits. The big one is cheaper. Big cheaper. And then on top of that, no moving parts, so it's less likely to break. You can set them up so you can use them in wet environments. You can set them up with built-in displays and reconfigurable buttons and all sorts of fancy stuff if you want. But the downside, they do need a microprocessor, and you have to program in the capability, so your development time is significantly greater than bolted in a switch. And then there is this no mechanical feedback, which I have to say, and I think all of us have probably experienced it, there's something deep down pleasurable for nerds to actually feel that little click of the switch, right? It kind of does something. I'm sure it's like if you ever watch a smoker when they're really desperate for a cigarette but they can't have one, they start playing with their lips and they start screwing around with their fingers, and they get this, I don't know, there's a lot of mechanical part of smoking that's part of the addiction. And anyway, and then touch buttons can be fussy in operation, like my refrigerator. They can be very irritating. And sometimes, in order not to get them too crazy, you may have to slow down the response time so they're not that responsive, because you don't want them, when somebody walks by my refrigerator, I don't want it dispensing water and ice, okay? So I want that to be pretty confident that yes, you do want water flowing, because hopefully you've got the glass there. And if it just triggers whenever somebody's in the proximity, that would actually make my bad interface worse. Okay? So there are some things you have to think about. We don't want to launch a missile towards Russia because some NCO leaned on the console in one of the missile silos, right? We want these things to be very clean and clear cut. That we do want to trigger register a touch. So sometimes we have to slow them down in order to get that. They obviously could be faster than a mechanical switch, way faster. You could hold your button and have it switch 100,000 times in a second if you wanted. But normally we prefer not to do that because that actually wouldn't work for our application very well. So there's a lot of pros and cons, and so you can make a bad interface with touch buttons. Trust me. Okay. So so in our PIC, so we do have this legacy capacitive touch sensing module, which we're going to use, and it actually works nice, and it's kind of fun to play with it. And we actually do have 12 potential touch buttons. There's only 4 of them implemented, so we only created 4 on the printed circuit board because we didn't want to go too crazy. We wanted to leave some pins for other stuff. The RC circuit actually creates a triangle wave. That's basically what goes onto the counter. It's really not a square wave, and it's not a sine wave. It's more of a triangular wave. And But you do have to dedicate timer 1 and timer 0 to this task, so you can't use them for something else now. You still have timer problem too. That's one of the reasons. Another reason why I haven't changed chips, because if I change chips, I'd want a chip that had 2 A to D modules, and there are some with them, but I haven't found one that really fits our purposes very well. So that's been another thing that's kind of slowed me down. But anyway, it does take 2 timers. And then, so here's the capacity touch sensing module. So here are our input channels, 12 channels all connected to different pins. And the pins are the exact same pins as the A to D pins. So if you use all 12 channels, then you have no channels for your A to D converter. So you can't, you know, you'd have to at least leave one of these unused in order to have the A to D converter have some kind of input. Well, unless it used the internal temperature sensor or something, you can still do that, I guess. And you select which one of these channels you're doing with these channel selection buttons, and then you also have to turn on the module. And so then you do have, there are some features of this module. They've jazzed it up a fair amount, trying to make it robust and really powerful and make it really competitive with other manufacturers' touch sensing modules. But they finally gave up because it just was going the wrong direction. So they have a lot of features in it where you can use internal references instead of the ground and power on the chip and other things. And you can actually use you can actually have the digital output converter. The digital to analog converter module can drive one reference, and your fixed internal voltage reference can drive the other reference. So you can actually have a very narrow voltage range that you're working in, which can actually help you with noise in some circumstances, but it doesn't fix this problem with fixed frequency interference. It's just the wrong frequency. All right, so anyway, and then this goes over here to timer 0 and timer 1. And the way this works, timer 0 counts some fixed module, and every time it overflows, then it goes down here and it stops timer 1. And then when you want to do another count, you zero out both timers, start them, and then select the channel you want, start both timers, and then when timer 0 overflows, it stops the count again. So each time you do that, your timer 1 count is collected over the same amount of time, the time that it takes timer 0 to count from 0 to 256. And then of course that time is determined by the clock. We're normally going to use FOS divided by 4, but you can always change FOS, and you can actually drive it with some other external clocks if you really want. And then you can actually not use it in the classic way where timer 0 is the time base and timer 1 is the counter. You can actually have timer 0 be the counter and timer 1 can be the time base, but it's a little harder because you don't have this built-in gate for timer 0 that you do for timer 1. So it works a little nicer if you use timer 0 and you have timer 0 turn off timer 1 when it overflows automatically. So you don't have to wait for software to detect that timer 1 overflowed, set the flag, and then you go and stop timer 0 overflowed and set its flag, and then you go stop timer 1. This happens, there's a direct wire running on the chip to go from timer 0 to the timer 1 module and shut it off if you've got it programmed correctly. And you have to set all these things up in the control registers for timer 0 and timer 1 and the capacity touch sensing ones. All right, so that's all there is to that. This is just a little more on timer 1. Remember, it's a 16-bit timer, so you can get bigger counts. That's actually helpful too. Whereas timer 0 is just 8 bits with a prescaler, so you can stretch out the period of time. You can make it longer, you can make it shorter. You want it long enough that you get a pretty good difference between touch counts and not touch counts, but you don't want it counting so long that it maxes out and overflows, and you don't want it counting so short that the difference between the touch and not touch is very small. So you want it, you want a pretty good count. And it gets connected automatically when you set the configurations in the various modules. It's hooked up then to the touch sensor module. Okay, and then here's the timer 0, and you have a fixed period for it. Normally you just let it run the whole thing from 0 to 255. When it overflows, then boom, that's when you stop timer 1. And so anyway, so we'll set all this up in the lab, and what you'll have to do is figure out the threshold to make the touch buttons work correctly. And the way the code has been set up traditionally, we've had one threshold for all the touch buttons, but I might set it up so we have a different threshold for every touch button. Although you can start with the same number and see if that works. But the other way we've done it traditionally in the lab, and I may change it if I have time tonight, although I may not, but you can definitely modify the code so that you can have well, the way it's been set up is if you touch, we had buttons A, B, C, and if you touched A and you didn't touch B, C, then you got a code of 1. If you touched B, then you got a code of 2, and if you touched C, you got a code of 3. But if you were touching C, it didn't matter whether you were also touching A and B, you'd only still get the code of 3. But you could set it up so that you can sense A and B and C as you're multiplexing, and remember whether all 3 are touched or only one of them's touched. And one of the projects last year was a group, was a guy who took the UTSA, and with 4 fingers he would touch the buttons, and then it would generate the 4-bit hex value. And it would display that in a 7-segment LCD. I mean a 7-segment indicator. And so that was pretty cool. So if you touched nothing, it would say 0. If you touched all 4 of them, it would say F, and everything in between. But to do that, you have to know if you're touching U and T, or U and S, or S and A, or T and S, or whatever. And you can't just check U and then check T and then check S and then check A. And if you're touching A, then ignore whether you're touching U, T, and S. That's how the code's currently set up. It's not that big a deal. But what we do is, on the fly, we set the channel number, and then we get the count, and then we save the count and check it to the threshold, and then we remember, okay, that one's touched, and then we do the next one. And then we only remember, oh, that one's touched too, so we forget that the first one was touched, and we remember the second one was touched. But we could set it so you can remember each one. I'll try and change the code to do that. So anyway, so that's basically touch sensing. Okay, let's talk a little bit about test. So I did create a little document that you can go through and kind of look at generically the stuff that, but I'll go through a practice test too. So let's talk about this first. So understand the registers used by the processor. Okay, so this is the programmer's model, right? So how many general purpose registers do we have on this chip? 1, the W register, right?
Oh.
That's it. 1. Now on the KL25Z, you're going to use at the end of the course for 2 labs. It has 13 general purpose registers. But we don't have those. We only have 1. And in the KL25Z, all 13 registers are 32 bits. Our working register is how many bits? 8 bits. That's it. Okay, how does the stack work on this chip? Somebody tell me, what kind of stack do we have? All right, so somebody's got to know this, I know. I mean, C uses the stack. We're not dealing with the stack directly. It's not a stack that we actually get to use. Even in the assembly language world, we didn't use the stack. Normally in the assembly language world, you use the stack all the time. And you have commands called push and pop to get things on and off the stack. We don't even have those commands on this chip, and that's because the stack, it's a weenie stack. It is only 16 levels. It's all set up in special hardware registers. It's not a stack that you can assign wherever you want in random access memory. And that's actually a bit of a liability for this chip. It's kind of one of its weaknesses. Most modern cutting-edge micros have a relocatable stack that's put in RAM. And just so you know, the way we normally do that is we take a block of memory. So here's say the RAM on say the KL25Z. So this is the KL25Z. So and it starts say at location 0 and it goes up to location say 16K. We normally then add our variables starting from the bottom up, but our stack we start at 16K and we work down. I got it upside down. I guess I should have it the other way. Just flip this over in your mind. So when you push, you subtract the stack pointer and then you write at the new location. subtract first and then write, subtract first and then write. When you pop, you get the value and then add one, get the value and add one. And so the stack pointer, this stack pointer can be reassigned wherever we want in memory, but normally this is where we would put it. If, however, we had an operating system, then we'd have a little space up here where we'd have the OS running, and then we'd have the memory cut up into other pieces, maybe 3 tasks, and we assign the stack here for each of those tasks, and then when we went back into our supervisor software, our OS, we would put the stack back wherever it used to be here. We'd remember that value and load it back in. And when you jump between tasks, you save the stack for that task and save the working registers and save the link register and the program counter, and then you jump to the new task and restore its stuff. And when you are in one of your local tasks and you create local variables, you actually create them not just randomly in RAM someplace, you actually put them onto the stack. You create them as part of the stack, and we call that whole picture of the stack with all the local variables and the saved values and everything, we call that your stack frame. And so that stack frame is typically how processes run and how OSs are able to shift between processes and preserve all the stuff between processes because you have a stack frame and you save certain parts of that stack frame and then certain parts you don't save. Okay, so be prepared to write a code segment to add or shift a 16 or 32-bit number. So on our little PIC chip, so first off, you're not going to have to write any code or no real programs. You've already had the programming test. And then as part of this test, this test is really the first half of a 2-part test 1. This is the written part, and then the second part will be an in-class practicum, where you're going to bring your laptop and your project boards into class, and I'm going to give you some extra parts, and then I'm going to give you an assignment, and you're going to group up into groups of 1, 2, or 3 students, and you're going to write code and show that it either works or fails. And that'll be your grade. So make sure you get your boards make sure everybody's got your board working. Come see me if it's not. Okay, so anyway, so you're not going to have to do this. This is old days. Understand the ways, okay, forget that this is PIC. Oh, I can't believe this is.
How old is that?
Yeah, that's old. Ignore this. Gosh, I didn't realize that. I had deleted that stuff. All right, be able to figure out how condition codes are affected by example instructions. So when you look at this, let's see, somewhere, oh, I guess it's in the example. When you look at the instruction set here, that's not it. Oh, here. When you look at this thing here, notice you can tell for every instruction how it affects the condition codes. Everybody knew that, right? Yes? No? Notice over here, status affected. These are the condition codes. So this add W to F, it affects the carry, the digit carry, and the Z bit. Those are the only 3 condition codes. This add W to F with carry affects the carry, the digit carry, and the Z bit. This affects the Z bit. This affects carry and Z, carry, and these 2 affect nothing. Okay, so make sure you know how to look at this. Here, this one, literal operations. The add literal to W and so forth. Subtract literal to W. These do affect the carry, the digit carry, and the Z bit. These affect the Z bit. These don't have any effect. So you should be able to look at this instruction summary, and you should be able to tell what condition codes are affected by what instructions. And remember, the move F instruction, it does affect the Z bit. So that's the one reason why you might say move port A, comma, F, where you'd leave the information there, but you'd be seeing if every bit in port A is 0. That's one thing you can do. And the Z bit would be set if all the bits in that word were 0. All right, so just throwing that in. All right. Okay, so instructions to be most familiar with. So, yeah, so basically, general principles embedded design. Microcontrollers, like in a laptop, differ from microcomputers, like in a laptop, differ from microcontrollers, like on the Viva board, because differences between using assembly language and C on a Viva board are So you should know kind of, so what are some differences between, say, your laptop and the Viva board? So microcomputers typically have a big motherboard with memory on it and some stuff to control for peripheral slots and maybe a graphics processor. But the actual microcomputer chip itself doesn't have any A to D converters in it. It doesn't have any PWM modules, doesn't have any capacity touch sensing modules, doesn't have any analog to digital converter or digital to analog converter modules in it. It doesn't have any PWM capability or capture and compare capabilities or comparators. It doesn't have any of that stuff. But a microprocessor does have that, right? It's got all these peripheral modules built in. So if you wanted to do those things with your laptop, you have to go out and buy something that plugs in through your USB port to do it. Whereas your microcomputer chip, you can find one that's got all that stuff built into it. So that's one of the main differences. Another main difference is typically, certainly the stuff we're doing with the 8-bit PICs, we don't use an operating system. So at any given time, our firmware is going to be written one time, and then we're going to run that program probably till we're blue in the face before we change it. In some cases, we might have the ability to push out updates to the firmware to the field, maybe. But basically, we normally have one program loaded, and that one program is going to run until our product is obsolete or no longer needed, or until we upgrade it in that particular case. So whereas on your laptop, you've got all sorts of programs running all the time in different threads, and then you're going to kill one program and boot up another and kill that and run another and kill that and run another. And you've got all this operating stuff running in the background, which, although we do have real-time operating systems for embedded controllers, we normally, at least at our little 8-bit level, we're not doing that. But on a fancier embedded controller, you might very well be running a real-time operating system. All right, so there's a lot of differences. For microcomputers, we usually have a lot of devices that allow us to have a robust GUI-type interface with a user. Whereas an embedded controller, let's say you make an embedded controller for a microwave. Well, you've got a front panel, a clock, and you've got some push buttons and some, you push this for popcorn, push this to heat up your hamburger, push this for, hot chocolate or whatever. But basically, you don't have a user interface where the user can type in, what's the meaning of life or something like that, right? That's something you have to do on your laptop. Of course, the truth is Google doesn't have a clue, but it'll give you some kind of answer. So anyway, okay, differences between using assembly language and C on the Viva board are. So you ought to have a little bit of a feel. If I ask you, so if all you want to do is set and clear some bits in some 8-bit fields, do you think you could write a more efficient program in assembly or in C?
Assembly.
Yeah, probably assembly would be easier for that. What if I want you to compute the area of circles of different radii?
C.
Yeah, don't even try and do that. It'll kill you. I mean, doing floating point in assembly is just like pulling teeth. Now, there are some microprocessors that have built-in divide and built-in hardware multiply, and they have divide and multiply instructions. So you could maybe do some of that. That was more old days, though. Nowadays, we're going to do those things in an advanced language and let it provide the 40-line routines to handle our floating point calculations or whatever. All right. So you should know kind of what's easy to do in C, what's really hard to do. If you're managing a project using an embedded controller, check all the things you'll likely experience. Well, okay. So what are some things that So first off, you want to make sure you are familiar with your integrated development environment. You want to make sure that you pick chips that have big families, so your next project can use something that's not too different than what you just did. If you pick a one-off chip in some obscure manufacturer and they don't have, that may be the only chip they make that has anything to do with that kind of application, and then you have another similar application, but that chip won't quite cut it, and you need a little more RAM or a little more programming space, you're done. Now you've got to go learn a whole new IDE and a whole new set of instructions and how the chip works, you're going to spend a lot of time that you could have maybe saved. So it's really nice to work with manufacturers that make a lot of different chips in different families, so you can migrate rather seamlessly. It's also nice to have good, robust, integrated development environments. They all have their idiosyncrasies and pains in the butt, I guarantee you that. But some of them are a little nicer to use. But one thing's for sure, once you're familiar with one, it's really a pain to have to learn another one. So again, good reason to pick one that's gonna be able to handle a number of different parts that might cover the range of the stuff you might be asked to do. And then, that may, best plans sometimes don't even work out, but it's good to try that. Obviously, when you're designing a project with an embedded controller, you've got some hardware considerations and you've got some firmware considerations or software considerations. You want to make sure that you keep in mind that the software part is probably the part that's going to get screwed up. And so you want to make sure, if you're the supervisor, you're keeping a sharp eye on the guys writing the code. You also want to make sure that you can allow the project to move forward on the hardware side even while the software is being written. And part of that key is you need to be able to put the code in your product after it's assembled. You don't want to have to, program the chips and then plug them in. You want to be able to plug them in place, especially if they're surface mount and soldered in. Obviously, it's really difficult to plug them in. And there are also sorts of a whole bunch of other considerations in terms of managing these things and how you test items, how you verify your design, a bunch of stuff. And I'm not going to ask you anything too esoteric, just good common sense stuff from things we've already talked about. Some questions about the part we've used, the PIC 16F1829. What's the range of voltages roughly that it can operate over? Well, it can go down to about a volt, a little maybe less than a volt, I guess, or 1.2, I forget. I don't even know off the top of my head, but up to maybe 5.5 volts. So if you know it's somewhere between about 1 and about 5, you'll be fine. We're running at 2 different voltages, 5 or 3.3, depending on the jumper setting that you choose. You should also know, have a reasonable idea of the various modules available to you. How many pins on this chip can you use for GPIO? Well, let's see. So you've got power and ground, they're gone. And then you could use the pins you're using for your PIC header, so that's port A0 and port A1. But if you're going to do debug stuff, you can't use them until you quit debugging your chip. So, probably, and usually if you wanted to use them, you'd have to set up so you could program the chip and then put a jumper on to connect those to the stuff they need to connect to, because those connections might very well mess up the programming. So you have to be a little bit careful with that. So if you take out those 2 pins, RA0 and RA1, and then the master clear pin, it can be an input, but you need to use it for master clear if you're going to use a debugger. Then basically you have, you're missing 5 pins, right? Power, ground, port A0, port A1, and port A3. So you're missing 5 pins. But all the rest of them you can use for GPIO with total impunity. And so that out of 20 pins, that gives you 15 that you definitely can use. So you don't have to know the exact numbers, but you should have a rough idea. How many pins is your PIC3 or your SNAP interface? Oh, by the way, so I know, so I talked about the SNAP thing. I know some people are sort of struggling with the SNAP. The SNAP should work fine as long as you have that low voltage programming bit set to on. And once you set it to on, from then on out, your SNAP should work just fine. If you set it off, the SNAP can set it off, but once it sets it off, it can't program it again. So you have to be somewhat careful with that. So you should just set that to on. We talked about the condition codes. We talked about the programmer's model. So you should know those core registers. And the ones I want you to know. So I want you to know the W register. I want you to know the program counter low, the program counter latch high. Remember, you can't write directly to the program counter. You have to do this indirect thing. You should know that the program counter is 15 bits, 8 bits in program counter low, 7 bits in the PC latch high. So that's the 15 bits. You should know about the BSR, 5 bits in the BSR, and you should know about the status register, where there's 3 bits in the status register that you're really interested in, and then there's a couple other bits that do some other things which I don't particularly care if you know or don't know. And then obviously there are a bunch of indirect registers which I've said you could basically skip, but that makes up essentially 6 more registers, because even though they're 16-bit registers, you have to do them in 2 4-bit chunks, 2 8-bit chunks, and then you have a reference to the 16-bit that's a separate name that doesn't really represent a register. It's just a name that you can use in the code, and then the hardware will actually use all 16 bits of that indirect register. So that's about it for that. You should know. So you should know that you have very powerful clock module. You can generate clocks in a lot of different ways. You can have an off-chip resonator, an off-chip crystal, an off-chip clock circuit that's actually driving the chip. You can have an on-chip clock, and it can be over a very wide range, from very slow to up to 32 megahertz. And all those are pretty programmable. So let's see. You should know a little bit. You should remember a little bit about your assembly language instructions. If you just have a rough familiarity with the code that you wrote, that's fine. Again, I'm not going to make you do a bunch of. I might make you write a mask or maybe one line or something, but that'll be about it. I don't think you have to write much more than that. So you should know that you should know something about the architecture of the chip. So you should know that it's a Harvard device. It has separate program memory and data memory, but the input-output is I/O map. So it does have an address in the data memory, and it uses the data memory address lines and the data memory data lines. You should know that of the 2 sides of the 2 memories, program memory, it's 14 bits wide, so it has a 14-bit data line, and it has it can be up to 32K in size in this family. So it has 15 bits of address line. On the data memory side, we know that we have 7 bits and 5 bits, so it's actually got up to 12 bits of address line. And then the data bus is only 8 bits. So 8-bit data bus, 12-bit address bus for the data memory and your modules. On the program side, 14-bit data bus and 15-bit address bus. You should know on our chip that we've got 8K of program memory and 1K of RAM, and then a bunch of special function registers for the various modules and whatnot. You should know that a few things are mapped to every bank, but that in general, most of the stuff we have to get to is bank specific, and the bank select register has to be pointing to the right bank. 5 bits of the 12 bits are in the BSR, and 7 bits of the 12 bits are in the instruction. So you should know that. Okay, let me go through the test. Let's see, I think I can try and see this. Yeah. Let's see. You should know we have 2 configuration words. You should have a rough idea of how those go down. With the change will be that low voltage programming now needs to be on instead of off. You should know the hardware stack, 16 levels. If you use all 16 levels, you're in trouble. I guess you can, if you use 17 levels, you're in trouble. 16, I guess you're still okay. If it overflows, it's going to overwrite one of your return addresses from the very first call, and so then you'll never get back to where you're supposed to be. So it'll definitely screw things up at some point in the program. And you can set one of the configuration bits to reset the processor if that happens. You should know what the watchdog timer does. You should know why we might want to use sleep mode. And then you should know a little bit about the integrated development environment. We can program it in C, we can program in assembler, we can set up variable windows, and we can set up breakpoints. We can program it for debug mode, and then we can single step it with a source level debugger. Now, what do I mean by source level? By source level, you actually get to sit there and look at your source code, and you can step through your program one line at a time. And we call that source level debugging. It's really, really nice. Back in the day when I used to, when I, wrote programs for various people back when I was a lot younger, I didn't have that. The only way I could do punch a button and have the computer print out its entire memory to the printer. And that memory dump was not all that helpful. Because a lot of times when the code had gone bad, what happens is it starts writing over the code part. This doesn't happen in a Harvard machine because you have separate program and data memory. But on a von Neumann, which that's mostly all I used, it would overwrite the program memory, which also was the data memory. And so then you would have, your memory would be, most parts of it would be all overwritten with junk, and you didn't know, you just couldn't make heads or tails out of what happened. You didn't even know where your program went bad. And so debugging things was really hard. The idea that you can sit there in single step and watch your program execute line by line and go out and look at different pieces of the memory and see special function registers and data registers change on the fly, it's truly amazing. It's really very powerful. So, and you can have watch windows where you follow variables. So you make sure you know about that stuff, and make sure that as you develop your skills, if you wind up actually doing this for, if you're developing firmware for a living or microprocessor-based applications for a living, you are going to need to be an expert at debugging, because that's typically what makes you lose sleep at night, is the software doesn't work. And sometimes it's the guys working for you whose software doesn't work, and you have to take them by the hand and help them to figure it out. So you need to have some skills with the debugger. Okay, so how many milliamps can the GPIO pin source and sink? 25 milliamps each way. But there is a difference when it's sinking current, that the composite current that's sunk goes through the ground lead and out. When you're sourcing current, it has to come in through the VDD pin. And so you have limits on the VDD pin that you don't have on the ground pin. So that's why we generally set up GPIO pins to sink current, not source it. What does the push button on the board do when you've selected master clear? It grounds the master clear. When you let go of the button, it pulls it up with a 10K resistor to VCC. The two voltage regulators on the board drop your battery voltage of 9 volts to either 3.3 or 5 volts. And you do waste a bunch of power in those linear regulators because they are linear regulators, not switching regulators. So you should know about the A to D module because we use that. You should know about any of the modules we've used in lab so far. All right, let's look at we'll look real quick at the test. This is a test from 2015, so it's a little bit old. So we'll just go through it as far as we can get. Okay, this question refers to the general principles of embedded design and microcontrollers in general. Check the things that are true. So microcontrollers, in general for microcontrollers, and not true for microcomputers. They have on-chip flash ROM. Yes, that's true for microcontrollers and generally not true for microcomputers. The peripheral bus typically requires a dedicated and separate controller chip. No, that's more true for a microcomputer. That's what the motherboard does. Whereas all of that is on the same chip in your microcontroller. Have several high-level human interface devices like a keyboard, a mouse, and a display. Duh, that's a microcomputer. Use disk drives to store the application software. Also, obviously, microcomputer. You could, I guess, hook up a disk drive to an embedded controller, but it would sort of defeat the purpose. Have a number of on-chip peripheral modules that can be configured by the user. That's a microcontroller. You've got all your built-in peripheral modules, and that's why you use these things, because you can do it all with one chip and save a lot of money. You're designing a controller for a toaster oven. The boss wants it to have a complex user interface with a time display, touch panel buttons, and accurate timing for toast cycle. What's the best statement about your choice of a microcontroller for the project? The micro should be an extremely low power device, even if this raises the cost of the project. Do you need extremely low power?
Not really.
No, I mean, you're not going to operate the toaster oven on batteries, okay? So, and what you're burning up in the heating elements is thousands of times bigger than what you're using to run your microprocessor. So it's a trivial part of the overall power budget of the toaster. The micro has to have a real-time clock as well as other timers, a touch sensing module, and enough pins to have to drive a display and other controls. Sounds good. You need a real-time clock if you're going to keep time, right? And you can obviously use that to time your toast. The micro must be very compact in size and have a very high-speed processor clock. No, why do you need that? This is a very simple low-level project. So you can, and you probably got plenty of space inside this oven. I mean, you know, it is an oven after all.
I forget the accurate timing.
You do need the accurate timing. So, right, so that would be selection 2. But selection 3 is not really relevant to accurate timing. I mean, the toast doesn't care if you're a few microseconds
Okay. Yeah.
off.
High speed, I guess it's.
Yeah. One major advantage that microcontrollers have over microcomputers makes them the best choice for embedded designs. Pick all the choices that represent an advantage for microcontrollers over microcomputers. Microcontrollers are much cheaper. Duh. Microcontrollers can have a larger amount of RAM. No, we normally don't do that. Now, microcomputers don't have it. They have you know, level 1 and 2 and maybe 3 cache, but they don't actually have the random access memory on chip. That's off chip on the motherboard. Microcontrollers have a much smaller footprint. Yeah, they don't have the, you know, the 900 pin socket with a huge cooling fan on top. Microcontrollers are much faster. No, generally not. Usually the microcomputers are much faster. Microcontrollers require fewer support parts. Absolutely. Yeah, big motherboards supporting with complex chips to support the microprocessor, the microcomputer, rather. You're designing a controller for a washing machine. The prior washing machine used a mechanical timer with many contact switches to trigger the various parts of each wash cycle. How many of you ever looked at the mechanical timer in a washing machine? Anybody pulled one out and looked at it? They're very scary things. It's got a clock module running in it, and it has maybe 30 pins coming out of it. And it, you know, you can pull it out and twist it, and it makes that sound as you do that. And they break. And they break because they're mechanical devices. The clocks stop working, the contacts get dirty. They, after all, are exposed to water and suds and humidity. So it's amazing that they last very long at all. So this timer was very expensive to replace and had a high failure rate. Is it reasonable to think that using a microcontroller for design is likely to reduce the failure rate? What do you think?
Yes.
Yeah, absolutely. You can probably hermetically seal the whole thing up so that it gets no exposure to the environment. And you know, once you get digital circuitry, as long as you don't have lightning strikes, it generally tends to work for a long, long time. Microcontrollers produced now often advertise their key features. Generally, producers strive to make micros circle the 3 best answers. Smaller, lower power, cheaper, fewer pins, fewer bytes of RAM, use higher voltage, more complicated instruction sets. Okay, what do you think? Smaller? In general, yeah. Lower power? In general, that's right. Cheaper? Yeah. Fewer pins? No, usually more pins. Fewer bytes of RAM? No, they tend to add more RAM. Higher voltage? No, lower voltage. More complicated instruction sets? Actually, no. We're going to the more RISC world, the reduced instruction set computers, and the instruction set for the HC12 that we used to cover in this class, it had almost 300 instructions, assembly language instructions, including dedicated assembly language instructions for fuzzy logic. Pretty crazy. It was nice.
What's fuzzy
But-
logic?
Well, the deal was, it was designed to be hand-coded in assembly. So their full expectation was you would never program it in C. So they wanted to make it, it had 6 divide instructions, 6 multiply instructions.
Oh, because it had to be floating point?
You had to be able to do some floating point.
Oh.
And the fuzzy logic instructions handled polynomials. It was crazy. And now you know, now 50 is about all the assembly language instructions you get. 50 or maybe 56, maybe 60 or less. And we'll probably go to more, you know, even less than that as time goes on. Okay, right. Which registers are used for indirect addressing? Okay, so I don't know, I probably won't ask you this because I told you you didn't really have to know it. But the FSR0H, FSR0 low, FSR1H, FSR1 low. Those are the ones in this. But you don't really. You should be aware of them, but I probably won't ask you that question. How many bits are used in the BSR register? And how many different memory banks can be selected with these bits? 32, right? Which register is involved in the movement of data to and from memory? W, yes. W is involved in everything dealing with data. Some of the core registers can have an immediate or local value written to them. Circle the 2 in this list that have this provision. Note there are actually 3, but only 2 in the list. So if you go down to this chart, literal operations. So if you look through here, most of these instructions use the W register. There are 2 which use 2 other registers. One of them is the MOVLB, which writes a literal value, a 5-bit literal value to the BSR. And the other is MOVLP, which writes a 7-bit literal value to the PC latch hop. That thing. Okay? So that's all there is to that. You should be aware of that. Okay. How many bits are used in the BSR? We did that. Okay, we did that. Did that. Okay. What is the function of the program counter? You should definitely know this. This is true for every computer under the sun, at least everyone I'm familiar with. Maybe it won't be true for quantum computers, but everything else. So what is it?
What's the next instruction you can execute?
That's right. Now, obviously, the truth is slightly more complicated than this because of pipelining, some other things. We're prefetching and blah, blah, blah. But you don't have to worry about that. This is a good answer. All right. If the LAT-A special function register in bank 2, what instruction would be generated by the processor directly bank cell LAT-A? MOVLW 0x02, MOVLP 0x02, MOVLW LAT-A, or MOVLB 0x02? That one. Is everybody clear on that? Raise your hand if that's confusing to you. Everybody's good? Okay. Okay, tell me why it's confusing. You don't know why it's confusing. It's just confusing. All right. So this bank cell is a processor directive. It tells the macro assembler to generate a special instruction. And what it has to do, it has to look up the register you specify in the bank cell instruction directive. In this case, what is the function register you've listed there? LAT-A, right? So it looks up and it sees what bank LAT-A is in, because it knows, because it's defined on the header file. And it finds out it's in bank 2. So what it then does, it creates a move literal to the BSR instruction and moves 2 to the BSR. So now the bank select register is pointing to bank 2. And that's what it's supposed to do, and that's how it works. Does that make sense? Yeah. Okay, perfect. All instructions take up the same room in program memory. True or false?
False. Very false.
How big is every instruction? 14 bits. So if every instruction is 14 bits, do they take up the same room? Yes, they do. No excuse for missing this one now. All right. I don't know, that may be on there in a slightly different form. Write the code needed to clear the special function register LAT-B. How would you clear LAT-B? CLRF, LAT-B. Do you have to bank cell it first?
Yes.
Yeah, you do.
Is there a master clear?
Well then, if there was, there'd be no more instructions executed. Given the variable A, B, and X are all in bank 0, location 20, 21, and 22 hex, write the code to swap. Okay, so this was the famous swap the instruction. I will not ask that. You've already had to do that. Now write the code to set the bit in lat A bit 3. I probably won't ask this either. But if you did, so there's several different ways you could do it. The easiest one would just be the bit set F lat A after you bank cell. Bank cell lat A, bit set F lat A, comma 3, right? Okay. I didn't really go over the, one of these days I'll go over the programming test. Okay, let's see, we're really out of time, but let me see if there's anything else we want to cover. Let's see. Yeah, so you should know about watch windows, source level debugging, breakpoints. You should know about look at the configuration words. We've only talked about certain ones of the bits in there, so know the ones we talked about. Yeah, so know the steps for setting up a new project, and know how you pick your tool chain, and then there's a few questions about labs. That's it. All right, we'll see. I won't see you on Thursday.